Okay, the one new thing today, I want to talk to you about what I call elevator problems. And what I mean by that is, suppose you're on an elevator and in your backpack you happen to have your handy dandy bathroom scale that you don't leave home without, because you never know when you might find a good elevator shaft and you might need it. So you're standing on your bathroom scale, and when the elevator is just there and you're impatiently waiting for it to move, FG will be acting down on you, your weight, and the normal force, of course, will be acting up. What the scale is going to read is the normal force. So the Fn is really the F scale. When you stand on your bathroom scale, anywhere, in any room, anywhere, it doesn't read your weight, it reads the force that the scale is pushing back with. But as long as you're standing there and there's no other forces acting on you other than gravity and the bathroom scale pushing back up, then obviously the scale minus Fg will be equal to 0 from the sum of the forces in the y direction. And so like what we've been doing for what seems like weeks now, so the scale, or our Fn, will equal our Fg. So when you're standing on a bathroom scale, just in a normal circumstance, the scale will read your weight. Okay? But now we're going to put the scale in an elevator, and we're going to make the elevator move. So now what's going to happen is when we do the sum of the forces in the y direction, the A in the y direction won't be 0. And what that means is the scale won't necessarily read your weight. Okay, so before we go there, perhaps you've been on an elevator in a tall building. Needs to be more than moving like one floor. But if you're on what we call a real elevator, going up 5, 6, 10, if you've ever been to the CN Tower or the Empire State Building or anywhere cool like that, where it goes up 20, 30, 100 floors, as it goes up, you feel your stomach moving. And it's because of what we're about to do. So let's suppose that we're going to accelerate upward from ground floor to like the 100th floor at a rate of maybe 3 meters per second squared. Now, obviously, you're not going to accelerate that whole time, but when it starts out, you'll accelerate, and then you'll travel at constant speed for some of that stretch, and then before you get to the top, you'll slow down, you'll accelerate in the opposite direction. So right now, we're starting on the bottom floor, so we're going to accelerate upward. And let's suppose your mass is 60 kilograms. So we'll do our sum of the forces, so it'd be our Fn. I'm just going to call it F scale to remind us that that's what we're finding. And it'll be minus Fg equals may. And so the question would say, what will the scale read? So you're looking for the F scale or the Fn. So take your may, take your Fg over, so minus Fg. And of course we know that Fg is equal to mg. So this is may minus mg. Now, because I put my Fg in as negative, it means I'm calling down negative, which means I'm calling up positive. So I can fill my numbers in here. So I have 60 kilograms times, when I take that over, it should become positive, shouldn't it? Times 3 meters per second squared plus 60 kilograms times 9.81 meters per second squared. And I already called my Fg positive, so I put my 9.81 in as, I already called my Fg negative, so I put my 9.81 in as positive. So this first term gives me 180 newtons, and this second term gives me 588.6 maybe. I'm just going to check it since you're not here to tell me if I'm right. Yes, 588.6 newtons. And so when we add those together, we get 768.6 newtons. So if my scale was reading in newtons, we would read 768.6 newtons instead of the 588.6, which we would have gotten up here when we were at rest, right? Because that's what my weight really is, 588.6. So this is often called our apparent weight. Our apparent weight because it's what we appear to weigh, but we haven't gained weight as a result of the elevator moving. It's just the bathroom scale is indicating that our weight is more. Why is it more? Because if we're accelerating upward, the upward force has to be bigger than what my weight is in order to balance my weight, to counterbalance my weight, and to give me a net force upward. Now, our bathroom scale doesn't usually read in newtons. It usually reads in kilograms. So we could find out what this is in kilograms by doing Fg is equal to mg. So m will be equal to Fg divided by g. So this 768.6 newtons divided by 9.81 meters per second squared. And yes, I am doing that in the calculator. And so you get a mass of 78.3486 kilograms. This would be known as our apparent mass. The scale would change so that, apparent mass. The scale would change so that it will be looking as if my mass has changed by almost 18.4 kilograms. Obviously it hasn't. Okay? So that's if it's accelerating upward. So if it's accelerating upward, the force upward then is going to need to be bigger than your weight. So what if it accelerated downward? In other words, maybe we're still on that elevator. Okay? So we're still on the elevator. Fg is still going down. Fn, which is our F scale, is still going up. Here I am, or here you are with your bathroom scale. Your mass is still 60 kilograms. You're still traveling upward, but this time you're getting close to that 100th floor. So this time your acceleration is going to be 3 meters per second squared down, because you're slowing down, right? You need to come to a stop when you get to the upper floor. Okay, so keeping in mind the question we just did, okay, with those givens, we're now going to do the same thing. Sum of the forces in the y direction is equal to MAY. There is still F scale going up minus FG going down, still equal to MAY. And notice now there's no x direction. We're still trying to solve for F scale. So, keep it in order. MAY plus FG, right? And FG, of course, is still MG. And again, we're calling down negative. And so now when we fill in our numbers, it will be 60 kilograms times negative 3 meters per second squared. And we already found this to be 588.6 newtons earlier. So now it'll be 180 newtons, but that 180 newtons will be negative, plus 588.6. So now my apparent weight will be 408.6 newtons. Okay, so this will be my apparent weight. And again, I can find my apparent mass by dividing by 9.81. So 508.6 newtons divided by 9.81 meters per second squared. And I get my apparent mass to be 408.6 divided by 9.81, 41.6514 kilograms. So now my apparent mass, my apparent weight, looks like I've lost, and that should make sense. If I'm accelerating downward, even though I'm moving up, then the upward force, the scale must be less than the downward force, right? My net force needs to be down, which means what's going up has to be less. Okay, so it's called apparent weight, apparent mass, otherwise known as elevator problems. And it's why when you start to go up, you feel heavier, and why when it slows down you feel lighter, and you feel your stomach moving as a result. Okay?